Let's summarize some of the main ideas that we've learned in this lecture. There's an important distinction between a path and a trajectory. A path is a spatial construct and tells us how we get from A to B through the world. A trajectory is a path plus a schedule and tells us how quickly we should move along the path, at what time we should be at what point along the path. It's important with trajectories that the position and orientation varies smoothly with time. We do this for a number of reasons. We want to reduce the maximum acceleration on the robot. It allows us to reduce the size of the motors, and it perhaps reduces vibrations induced in the structure of the robot. What does smooth mean? Well, it means that the position is continuous as a function of time, and velocity is continuous as a function of time, and we would hope that the acceleration is continuous and perhaps the jerk is continuous, and so on up through higher order derivatives. In robotics, a common technique for generating a trajectory is to use a polynomial, typically a quintic polynomial which has got 6 coefficients, which lets us independently specify 6 boundary conditions: the initial and final position, initial and final velocity, initial and final acceleration. And we can write this simple matrix relationship which gives us the coefficient values as a function of the trajectory time, capital T, and the boundary conditions. There is, however, a performance problem with polynomial trajectories, and that is that the peak velocity is almost twice the average velocity. And we're wasting motor performance and effectively taking twice as long to get where we want to get to. So a more efficient trajectory is what's called the trapezoidal profile, where we have some acceleration phases followed by a coasting or constant velocity phase, followed by a deceleration phase. A slight disadvantage of the trapezoidal profile is that the second derivative, the acceleration, is discontinuous, but it has many other virtues and very commonly used in robotics and machine tool control. If we want to move from one point to another through a few intermediate points, which we call via points or waypoints, then in order to achieve continuity in the path, we need to introduce what are called blends, and they're shown here in red. We introduce an acceleration period to transition from the velocity heading towards, for instance, point 2 into the velocity we need to head towards point 3. A disadvantage being that we never actually get to the point that we're heading for. If the acceleration time is small, we get very close to the via points, but the acceleration on the machine is high. If acceleration time is large, then the acceleration of the robot is low, but we miss the via points by a larger amount. We introduced the notion of interpolating between an initial value and a final value based on a scalar s, which varies between 0 and 1. 0 gives us the initial value, 1 gives us the final value, and 0.5 is halfway in between. X can be a vector, and if s is a smooth function of time, then so is x. We talked about how we cannot apply this simple interpolation scheme to rotation matrices. Rotation matrices are special, they're orthogonal matrices, so adding 2 of them together does not result in another orthogonal matrix. So we don't do this to rotation matrices. Instead, what we can do is convert our rotation to a set of angles. It could be Euler angles or it could be roll pitch yaw angles, and we can interpolate those. We introduce the direction problem. When we're interpolating an angle from an initial value to a final value, it's important to remember that there are 2 ways we can travel around a circle. We can travel the long way, which is shown here in blue, or the short way, which is shown here in red, through the value of theta equals pi. We can interpolate quaternions. We need a more complex formula in which to do this. The interpolation, once again, is a function of s, and s varies from 0 to 1, and an important parameter in this interpolation is theta, which is determined from the parameters of the initial and final quaternion. Quaternion interpolation provides the shortest and most direct path between 2 orientations. This figure shows the position of the tip of a vector which is undergoing different types of rotational interpolation. The white path is due to quaternion interpolation, and it's just mentioned it's the shortest and most direct path. We can see that the Euler angle and roll pitch yaw angle interpolation paths deviate from that. That means that they take a longer and more indirect path between the 2 orientations. Finally, we come to pose interpolation, often referred to as Cartesian interpolation. We have 2 poses, pose 0 and pose 1, which are each represented by a rotation matrix and a translation vector. We can convert the rotation matrix to a quaternion. Interpolating the translation is very simple. We apply linear interpolation to the translational component, and then we apply quaternion interpolation to the rotation component. We can convert the interpolated quaternion back to a rotation matrix, combine it with the interpolated translation to rebuild a homogeneous transformation if that's what we want.